Hello, this is just going to be a very basic, quick and dirty explanation of how to do the simplex method. It's just going to be the mechanics behind it. It's not going to be any of the theory and not even much of the terminology. So I'm just going to jump right into it. Let's say we want to maximize a function, and let's get out this function that we want to maximize. There we go. So we want to maximize this function. Subject to these constraints. Now this is going to usually be given to you in some sort of word problem, like x1 is the number of toy cars that you sell, and x2 is the number of toy trains that you sell, and this is the price of the toy cars, and this is the price of the toy trains, and you want to maximize this function, but these are your limits. So these first three limits are going to be used in the simplex method. This last one is called the non-negativity constraint, and we don't care that much about it because when we use the simplex method, we're presupposing that it is non-negative. So I'm just going to take it right out. If you don't have that non-negativity restraint, that means that you have a different you have to solve it in a different way. Also note that these are all less than or equal to. If it were greater than or equal to, if any of them were greater than or equal to, or just plain equals, then you would have to do some extra steps. This is, like I said, just the most basic form of the simplex method. There are more steps if you have a different type of problem. But the first thing I want to do is rewrite these equations in a way that's just a little bit easier to see, so I can know like what the columns I'm going to be dealing with are. Yeah, like this. So I've separated this into, not really separated, but I've made it so that you can see this is the x1's column, this is the x2 column, and this is the right side. Now, I want to take a look at just one of these constraints right now. The maximize, we're going to come back to later. So for right now, I'm just going to delete the maximize. So then for this one right here, I'm going to take a look at just one of these. So I'm going to take a look at this first one right here. Notice that this is a less than 0, so that means that here, let me rewrite it down below. That there's going to be some. Here. There's going to be some type of new line. Okay, here we go. So since this is a less than 0, there's going to be something that when you add to it, it'll make it 0. So that means that we're going to call that something plus S1 that will make it equal to 0. So this plus S1 makes up the difference. We call it S1 because it's a slack variable, so we just call it takes up the slack that makes it from less than 0 to 0. And this is for the first constraint, but we can add it to all of our constraints to make our constraints look like this. There we go. So move over a little bit to the right. So these three constraints, you can see them in blue here, are now equalities instead of inequalities. So now that we have it in this form, we can put it in a matrix. So our matrix is going to look like this, and I'm also going to add back in the z line right here. This is the equation that we're maximizing, but I'm going to get to that in just a minute. And this, I should not have deleted that first one. I'm going to add that back on just so you can see how it goes from one to the other. There we go. Okay, so you have this negative 0.2 times x1. So this is the x1 column. This is the x2 column. Notice that there's a 0 here because there's no x2 for the third constraint. And then now all this stuff here, these are the slack variables. And notice that they make the identity matrix right here. And then, of course, your right column. Now, this right here is your 0. Let's see if I could find the... here it is. The original equation. This is the function that we're trying to maximize. There we go. Okay, so this one is going to go down here, but also notice that this is going to be the opposite of it. We have a negative 20 and a negative 50. That's just part of the simplex equation. Technically, this is supposed to be z minus 20x1 minus 50x2 equals 0, because you're just subtracting 20x1 and 50x2 from both sides. So sometimes from some books you'll see a extra column on the right. They'll have like a 1 here and zeros here, but most books will just leave it off because it's kind of useless. It's not actually something we ever use in the simplex method. At least not in this basic part of the simplex method. Okay, just a little bit lost. Let me catch up. Okay, so let me get rid of all of this stuff. So hopefully you see now where this matrix comes from. And so I'll just take out the stuff that we don't need right now. So I'm going to assume that you already know how to pivot around an entry in a matrix, because if you're doing the simplex method in your class, I assume that you have already done things like reduced row echelon form of a matrix, which is actually, in terms of what you're doing with matrices, that's quite a bit harder than this is, because you don't do quite so many pivoting in this as you do in that. But the trick for this is figuring out where do you pivot around, like which entry do you use to pivot around. You can kind of see that I'm already hinting at it'll be this one, but that's actually wrong, because I just realized that's not right. So the first thing we do to find out which entry we pivot around is we take a look at the 0. Then this is 0, not to be confused with 0. This is just called the 0 because it is the maximization that we're doing is going to be z. We just call it x1 plus blah blah blah, all that stuff equals z. So when we try to find what entry we're pivoting around, the first thing we do is we look at the 0. And we look at what is the most negative number in the 0, and that is negative 50, because negative 50 is smaller than negative 20, or less than, or whatever we want to think about it. So that means that our pivot entry, our pivot element, or whatever, is going to be in this column right here. But obviously we need to know which row we need to pivot around to. So the way we do that is we divide this column by this column on the right by our pivot column. But we want to skip, we only, for this pivot column right here, we only care about positive numbers. We don't care about 0, and we don't care about negative. We don't have any negative numbers here, but if we did, we just ignore it. So so for this top one, we have 0 divided by, oh, that's not right. Oh, okay, here we go. 0 divided by 0.8, which will just equal 0. Right? Does that make sense? That should make sense. So, and then 240 divided by 4, and I just did this a second ago and I forgot. 240 divided by 4 is 60. And for this one right here, we skip it because it's 100 divided by 0, and you can't divide by 0. But now that we've discovered which, okay, so now we know which pivot column it is. We divide this by this. We find which row we want to pivot on by looking at the smallest entry here. So we have 0 here. 0 is smaller than 60. So we go by this. This is the entry that we pivot around. So I'm not going to bother showing you the individual steps through the pivot because I'm strapped for time and I keep rambling. So I'm going to just go ahead and show you the next step. Once you pivot around that point 8, this is the resulting matrix. But we're not quite done because we still have this negative 32.5 here. It's the only negative entry, which makes it the most negative entry. So we go ahead and pivot from this column. So we ignore this entry here because it's negative. Don't forget that. You want to ignore it. Even if it's 0 over here, we still don't care because it's negative entry there. So we do 240 divided by 3, which will give us 80. Oops, got the equal sign. Okay, there we go. 240 divided by 3 is 80. And we also have 100 divided by 1, which is equal to 100. And of course 80 is smaller than 100, and we're pivoting in this column, of course, since you got to know the 3 and the 1. So then you have this entry is when you pivot around. So when you do that, you will your resulting matrix will look like this. Okay, so here we go. So now we need to know how to interpret this. We're done because there are no more negative entries here. But we need to figure out how to interpret this. It's pretty similar to the way you would interpret a reduced row echelon matrix, sort of, but not quite. We only care about the columns where you have a 1 and no zeros left. So it's just 1s and 0s. If you have two 1s in a column, then that's not the one you care about. In this case, you have 1 for this first one, this x1, because this column corresponds to x1. So you have x1 equals 80. So x1 equals 80. And then you have x2, because this column corresponds to x2, and this goes to this row. So you have x2 equals 20. And since these two columns don't have anything, I'm going to decrease the space between those two. Oh no, who cares? Since these columns don't look the way these do, since they don't have the 1s and just 1 1 and all the rest zeros, we're going to assume that they're all equal to 0. So we have, that should be S1 and S2. Wait just a second. S2 equals 0. And this one right here, this is slack variable 3. So slack variable 3 is going to be equal to 20. But these are all slack variables. We don't really care about slack variables because they're not an objective part, well, not objective, they're not a physical part of the problem. They're just dummy variables to make the procedure work. So I'm just going to get rid of them. But then this last part here is very important. That is telling us what the z value is. Because when x1 is equal to 80 and x2 is equal to 20, you're going to have 2600 as your final answer. This is what we're doing, is we're maximizing the value. So this is the maximum possible value for z, and that happens when x1 is 80 and x2 is 20, and that is the end of the problem. I hope that's helpful. I know that it's very quick and very dirty, but this is not meant to be exhaustive. It's just supposed to get you started, and from there hopefully you'll be able to get some of the other more advanced things, like if you have different kinds of constraints, if it's a greater than or if it's an equal to. So from there, hopefully this will help. Thanks for watching.